Now we move on to the independent or unpaired sample t-test. Here, we're looking at where the data sets that we're comparing, we say there's no relationship between them. They don't have anything in common. So they are not dependent. Now, the example we're using here is a randomized randomized control trial where we assign one group to a treatment and the other group to another treatment of placebo. So here we can test the null hypothesis of saying there's no difference in group 1 and group 2, using the independent sample test. And you have a formula in there where we could talk about saying the mean of 1 versus the mean of 2. That's the difference between the two groups divided by the standard error of the difference between the two groups. Now, this is not so different from what we had just done from the paired t-test. The differences we will explain in the next couple of slides, and it has a lot to do with assumptions we make about the standard deviation. So I see a question coming in if there's an implication if the confidence interval level has negative. No. So what the main thing we focus on is not whether it's negative or positive. What we're focusing on is whether it crosses our null value. So you pay attention to whatever your null value is. If it crosses that null value, that's when it has an implication where you fail to reject your null value. So say we assume that the standard deviation, that the population standard deviations are equal between the two populations we're looking at, we can go ahead estimating a weighted standard deviation using the formula that you have on your screen there, where the degree of freedom here is a little bit different from what we've seen earlier on, where we said this n-1. Here we're saying is the n from sample 1 plus n in sample 2 minus 2. Now, scenarios where we can assume equal standard deviations are if the study suggests that the two groups are similar. If one standard deviation is more than double the other, we cannot make that assumption. Then another thing we can look at is the test for equality of variances. So I see a question talking about when there are more than 3 groups. We'll get to that. But one thing you should note, since you're asking the question at this point, is that as much as possible, do not use t-test for when the number of groups are more than 2. So say because most of the time we do not know all the characteristics of the data, it is generally safer for us to assume that they are unequal. So leading us to a different set for that, a different formula for that, for the unpooled one, which you have on your screen here. And the degree of freedom here is a little bit more complicated than and outside of the scope of what we're going to cover today. So in this particular example, we're looking at a clinical trial where we randomly assign women into daily iron supplementation or a placebo to assess whether the supplementation increases hemoglobin at the time of delivery. Now, we got ahead to be told that only 982 out of our initial population of 1,500 were identified at the time of delivery, and that the others either had a spontaneous abortion or did not return to the hospital so we can take measurements. we are provided with some outputs in front of us. So in this outputs, you see, let's focus on the group statistics first of all. If you look at iron tablets, those with 1 means they received the supplementation, with 0 means they did not. So we look at the sample size 481 and 541, and we look at the mean in here, where we provided a mean for the group that received the intervention as 11.75, and for the group that did not receive the intervention as 10.92. We have other test statistics in there. Then the question is, what do you think we'll use here? Equal or unequal variances? What do you think is the case here? Anybody willing to take a stab at that? Okay, I see. Okay. Okay. So I for those saying unequal variances, yes, that's what we'll go with here. Now looking at sorry, I'm getting distracted by your test, but I'll leave that to Larry to continue going through. So we go to the results, interpretation of the results, and look at it to once again to go through it to see what the mean difference in hemoglobin was at the time of delivery. Remember, as usual, our null hypothesis is usually there's no difference, while the alternative is there's a difference. And then we look at this to say the mean difference at delivery is 0.83, and that's greater than 0. Sorry, let's go back to the test statistics. Okay, that's the mean difference here, 0.83. Okay, so sorry, I wanted to be sure it was the same slides on both pages, right? So and if you're looking at it again, remember what we talked about when someone asks what is the significance of when it includes 0, and I indicated that what we're paying attention to is what the value for our null hypothesis, and the value for our null hypothesis is 0 in this case. So when it includes 0, what we do is we fail to reject the null, right? But when it does not include 0, whether it's negative or positive, we'll go ahead and safely reject the null and go with the alternative. And in this particular case, if we look at our 95% confidence interval, the lower and upper ranges, it does not include 0. So we go ahead and confidently reject the null that there's no difference and go with the alternative. And if we also go ahead and look at the p-values, we see that the p-values are highly significant. So our fourth example here is, say, assume you hear 2 of your colleagues arguing about whether the number of hours worked among 2 different groups of resident doctors are different on the average, and we have the data, or even if you make the assumption that this was about pay, whether male and female alike are paid equally, and the data is there, and you're trying to look at to see if this is statistically different or if or not. Once again, we're given the group statistics where we told the sample size for female is 62, and the sample size for male is 125. And we go ahead and we provided the mean and other test statistics here. And I go ahead to ask again, whether we use equal or unequal variance here. I see questions about equal and unequal variance, keep coming up. So I'll take us back to this, right? Who can remind us of what the formula for how we can calculate variance is? Who can remind us the formula? Someone? Any volunteers? The square of the standard deviation. So when we're talking about meaning it is dependent upon the standard deviation. And we look at the assumptions that we've listed on your screen here, where we talked about when do we assume equal standard deviation, right? And we're talking about the design of the study suggesting that the groups are similar, right? As being one scenario where we do it. And in scenarios where we do not make that assumption is where one standard deviation is more than double the other. And really, where there's no suggestion about the two groups being similar or not, or where you cannot look at the standard deviation to know if one is higher than the other, that it's usually safe for us to go ahead and assume that they are unequal. Does that make sense? So we come back to this particular example, there's really nothing in here that makes the suggestion that the standard deviations here could be equal, right? Yes, we see the test statistics and see that one is higher than the other, but not necessarily double. So just like we mentioned on the last slide, it's usually safe for us to assume unequal variance really in here. But as you can see, if you're looking at the test results that are being put out from SPSS that is on your screen, you see it gives you both the results from when if it gives you both the results for when you make either assumption, whether equal or unequal variances here. So, and if we look at this as usual, null hypothesis will be there's no difference in the mean. So meaning 0, while our alternative will be anything but 0. And if we look at the mean difference there is a negative value, negative because of we're saying female minus we're saying female minus male, and we end up with negative 6.58, which is different from 0. So as usual, at the same conclusion we made in the previous examples, that 0 is not included in our 95% confidence interval, so we can safely reject our null hypothesis and conclude that female residents worked significantly fewer hours than their male counterparts. Now we go back to that scenario where somebody had asked that what do we do when there are more than two groups to be compared? And that is where we move into ANOVA, which is analysis of variances. So t-test doesn't do well comparing more than two groups. So, and that is where this comes in handy. And there are certain assumptions that that come into using ANOVA. One is that this is a normal distribution, or that the sample size is large enough, at least more than 30, I believe, and that the standard deviations are approximately equal, and that these are independent samples that we're talking about. So where those conditions are met, we can go ahead and use this to calculate the differences. Now, one of the things to note is that unlike the t-test where you're able to say one group is different from the other, what's in doing the analysis of variances, what we can only say is that the groups are different. We can't exactly say it doesn't exactly tell us this group is bigger than the other or that group is lesser than the other. It just simply goes ahead to tell us that the groups are different. We already went ahead with this to say the only part we've not covered here is the null hypothesis and the alternative. So in the null, it's saying everything is same. In the alternative, it's saying everything is not the same. And it allows us to compare multiple groups. And remember, again, it doesn't tell us which group is different, which group is higher than the other or lower than the other. It just simply tells us that the groups are different, that they are not all the same. So here we can start talking about where the variabilities are coming, right? And because all this plays into impacts our results in one way or the other. Are these differences, variabilities, is it within the group or between the group, right? So because ANOVA assesses how much variability is due to the differences between the groups. So if there's any within group variation that is in play here, it impacts our outcome at the end of the day. So we go back to variance, standard deviations, and reminding ourselves, that our variance is a square of our standard deviation, and putting up, paying particular attention to the numerator, which is a summation of the differences, right? Here, introducing a new concept here, which is the sum of squares, which is summation of the squares of the differences between the mean, the population mean minus the sample mean, or the observed mean minus the expected mean, depending on what populations we're looking at in here. We can go ahead and say the sum of the squares, we can put them into two parts. The sum of squares due to differences between the group means. This is what we're really interested in here, or the sum of squares due to difference between the observations within the groups. Now, this is the residual sum of squares. We're not going to really delve into that in here, right? So one other important thing to point out here is that the ANOVA is based on the F-test statistics, which we saw in the last slides. Which we saw in the last slide that we had addressed. So we jump into our first example. I say, for example, you're interested in comparing the mean systolic blood pressure of patients managed by 3 clinical groups, and then you randomly assign them and measure their BP at time 0 and at 6 months of follow-up to identify what the optimal strategies for hypertension care would be. Now, say the mean for group 1 appears a little bit higher than that of the other groups. And you run your ANOVA. You run your ANOVA and you end up with the test statistics you see in front of you, telling you what the sum of squares of between the groups are within the groups. and then giving you what the total is. Now, between the group is the degree of freedom. As you see on the previous slide, is usually n-1. So that ends up with 2. And within the group, it's a little bit, it's the sum of all the n's, then minus the number of n's. So which number of groups, which in this case gives us the 897, which we're seeing in there. So, and this gives us a two-sided p-value that is highly significant. So in this case, we go ahead and reject the null hypothesis that there's no difference and conclude that they are different. So remember I had mentioned at the beginning that, it tells us there's a difference, but it doesn't tell us what that difference is, which is higher, which is lower, and what their relativity to one another is. And that's where we come in with the BONFERRONI correction, right? Which you could do to compare each of the groups against one another to see how they are relatively different from one another. So with that, you can help to be able to make the conclusion to say group 1 is higher than group 2 or group 3 is less than group 1. So I see questions about one-way, two-way coming in, So all the examples, one thing to note is that all the examples that were used previously refers to the one-way ANOVA, right? And but sometimes we may want to look at 2 or more categories and talk about two-way ANOVA. Now that's not being covered here today. The idea here is just to introduce you to the concept of comparing more than 2 groups. Okay, so and our focus up to this point has been strictly on data sets where we can approximate a normal distribution. That's been our focus here. And so all the tests we've looked at fall into parametric tests, the category called parametric tests. Now, what of scenarios where the conditions for the normal distribution are not met, the parameters for normal distribution are not met? Those scenarios are outside the scope of today's session, but I just thought to just use one slide to highlight that for every single parametric test we've mentioned today, that there's an equivalent non-parametric
Someone
test.
has a question. So I'm just giving out the chance to can you please ask your question?
All right, so thank you very much. About whether we use equal or non-equal standard deviation. You said we should assume that they are equal standard deviation if one standard deviation is more than double the other standard deviation.
No, that you cannot assume equal if one is double the other. You cannot assume equal. That the easiest way you can assume
equal if one is more than double the other.
Yes.
Okay. In that example 3, we have the standard deviation, and I don't think it will be double. I'm thinking it should be equal, not unequal. I don't know. It's really confusing. In example 3,
you're referring to this?
Yes, sir. The standard deviation here for group 1 and group 0, 1 and 0, if you compare, it is not double. So I thought then we should not assume.
So, okay. So, when you, what did we say the again, what did we say is the formula for variance?
Variance, the standard deviation.
The square of the standard deviation, right?
Yes, sir.
Okay. So in scenarios, there's something in the study design that makes you believe that this is equal, it's usually safest for you to make that assumption that they are not equal. Now, if you have the details, the other way for you to look at it is if you already have the details to calculate the variance for both groups, you go ahead and calculate the variance for both groups and see if they are truly equal. Now, in here, we have, remember that if you're doing this on your own, right, you don't have those group test statistics. You have to like calculate them to determine them, right? So,
yes,
but in this particular scenario where you have the group test statistics available to you, how about you do the calculation and you tell me if you still think the variances are equal in this particular case?
So when we talk about being equal, doesn't mean it have to be exactly the less than double the other.
Okay, so let me flip it in the other way, right?
Yes, sir.
Why do we need to use a test to determine if 11 and 10.9 are the same? Why do we need a test to determine that? Because we want to eliminate all subjectivity, right?
Yes, sir.
Okay, so look at it in that same way, because if you look at the variance in here, your variance for the group that did not receive the intervention will be coming up at approximately 3.6 or 3.6 something,
Yes,
whereas the
yes,
variance for the people who received the intervention will be
Maybe
coming
around
up to about exactly.
about 4.
So, okay. So would you be still making that assumption that they have equal variances?
That's one thing I wanted to clear, sir, because from what I read in the slide, they exactly the same. Just said if it's more than double. So double of that one of the 3.85 should be around 7 point something.
Okay. So
it's
I think this is the confusing slide here. This is the confusing slide here.
Yes,
What you should just pay attention to is the point number 1 in here, right? If there's nothing in the study that makes that suggestion, just go with the assumption of unequal variances. Is that helpful?
All right, sir. Thanks.
Okay. So we are at the end of today's session. I'll just take questions. If other individuals have questions about what we've gone through today, we can go over it. Just for me to conclude on this slide before the question starts coming in, is that one of the things that you should note is that the non-parametric tests, while they are not as the conclusions we draw from them are usually not as powerful as what we draw from the parametric test, and one of those reasons is sample size. The non-parametric tests are amenable in places where the distribution is not normal and where the sample size is small. So they're a little bit more flexible when you start getting into sample size issues. So it's just one thing to note.